Okay, so let's talk a little bit about today's lab, which is the Bleach Lab. This is a 2-day lab, and it will take the entire 2 lab periods. It's an hour-and-a-half long series of videos. So first things first, let's talk about what is bleach. Fundamentally, what is bleach? The stuff that we use a lot in everyday life. It is sodium hypochlorite. And the principal active agent is our hypochlorite anion. Now, the way that bleach is generated commercially is from chlorine. Now, you may ask, why don't we just use solutions of chlorine? Well, that's pretty dangerous to handle in everyday life, and there have been a lot of incidents where people have mixed bleach with incorrect chemicals and accidentally generated chlorine and other toxic gases. So bleach is made from chlorine under basic solution. If we take a look at our oxidation numbers, remember that oxidation number is the quote-unquote theoretical charge, assuming all of our bonds were ionic in nature. We start off with chlorine with an oxidation number of 0, and we generate hypochlorite where we have an oxidation number of +1, and chloride. Would someone like to tell me, and let's try to justify this answer, what is the charge of chloride? What's the charge of chloride? And don't be shy to type in the chat. And this may seem and don't overthink this too much. Okay, perfect. So what would the oxidation number be if the oxidation number is the theoretical charge? Is it also going to be -1? Essentially, if the oxidation number is treating all of our compounds as if they're ionic compounds and calculating the theoretical charge of each atom, the charge of just an ion given is the exact same as the oxidation number if it's of that atom. So for example, chloride has a charge of -1, so its oxidation number is -1. Let's do the same thing for hypochlorite. So we have ClO. Okay, so oxygen's typical charge is -2. So then, what charge of chlorine must we have in order to get a total charge of -1? What charge do we fill into the blank here? What charge do we put in that blank spot? +1, exactly. And that's why our oxidation number, our theoretical charge of chlorine, is +1. Does that make sense to everyone? Does that make sense to everyone? Does everyone remember this discussion of oxidation numbers from the worksheets that we did? Okay, so from here, we can break up this reaction into oxidation and reduction half reactions. This is purely to show that when chlorine gets oxidized to hypochlorite, it loses electrons. And when chlorine is reduced to chloride, it gains electrons. And we have 2 electrons lost in total. If we add our equations together, we get the following equation, which is exactly the same as in your lab manual. One thing that's really interesting about this reaction is we have chlorine going to the +1 oxidation number and the -1 oxidation number in the same reaction. We call this a disproportionation reaction. Don't sweat the name too much. The main thing that we're going to take away is we now have a chemical equation and we can talk a little bit about stoichiometry. So I'd like you just to think about with me, what is our mole ratio for the moles of hypochlorite generated per mole of chlorine reacted? What's our mole to mole ratio for this reaction between chlorine and hypochlorite? What's our mole to mole ratio from chlorine to hypochlorite? 1 to 1, exactly right. So in order to standardize, since bleaching agents and many cleaning agents won't use just hypochlorite, they may use another chlorine equivalent. We'd like to describe bleaching agents using available chlorine equivalents, which is essentially the moles of chlorine present per mole of bleaching agent. In this case, it's a 1-to-1 ratio. So in effect, by measuring the grams or moles of hypochlorite, we can determine the chlorine equivalents. Does that make sense so far? Okay, so what you're going to ultimately report is the percent mass over mass of chlorine, which is the grams of chlorine per gram of solution or solid, depending on what bleach sample we're titrating. We're going to titrate both solid and liquid bleach. If it's a liquid bleach solution, we can get the mass of our solution by taking the density times the volume. Now, the next question we need to address is how can we find the moles of hypochlorite in a bleach sample? How do we do that? Well, to accomplish this, we're going to utilize the techniques of redox titration and iodometry. So, the key word here is we're fundamentally doing a titration, okay? And the only twist is we're doing a titration using techniques of iodometry. So what is iodometry? We're using defined reaction, in this case of iodide, to generate iodine. The iodine is then titrated to determine the concentration of our unknown reactive species. So you may ask, why iodine? Why iodine? So fundamentally, our iodide is going to react to make iodine, and we're then going to titrate the iodine. So we're titrating the iodine generated. So under acidic conditions, iodine is generated via reaction of iodide with hypochlorous acid. So this is our bleaching agent to generate chloride and iodine. And the iodine is what we'll be titrating. Now, when iodine is generated, iodine has this distinct brown color. So iodine is really easy to detect and visualize. That's why we use iodometry. Iodine is very easy to titrate, monitor, and visualize. So iodide is being oxidized, and our hypochlorite in bleach is being reduced. Now, just like before, even though this is a redox reaction, what is our mole ratio between iodine and hypochlorite? What is our mole to mole ratio between iodine and hypochlorite? Is it 1-to-1, 2-to-1, 3-to-1? What is our mole ratio between iodine generated and hypochlorite reacted? 1-to-1 also. So we know fundamentally that the moles of hypochlorite that we start out with are equal to the moles of iodine in solution. And we're going to figure out the moles of iodine in solution via titration. Now you may ask, why bother with iodine? What's so special about iodine? Well, it has a lot of perks. So first and foremost, it's colored, it's easy to detect, and it's relatively stable. Now, the principal detecting agent that we're going to use is that iodine and iodide in solution make the triiodide ion. And in the presence of starch, we generate this beautiful iodine starch complex. And the nice thing about it is it's self-indicating. It's this deep blue color. And when the color disappears, the endpoint is reached and our I2 has completely reacted. So we can visualize whether we've completely reacted all of our iodine by the disappearance of this deep blue color. Now, so iodine is easy to titrate and we can detect even very minute amounts of iodine. So it's wonderful to titrate and it's quite beautiful to look at. So we've generated iodine from our bleach. We're then going to titrate the generated iodine, remember, from our reaction with our bleach. We're going to titrate our generated iodine with sodium thiosulfate. And just like before, we can view and we can write out oxidation and reduction half reactions. I'll leave it to you to double check the oxidation numbers, but essentially our thiosulfate is acting as our reducing agent and our iodine is being reduced back to iodide. Now, looking at our chemical equation as written, looking at this chemical equation here, can we figure out the relationship between thiosulfate and iodine? What's our mole to mole ratio of iodine present to thiosulfate reacted? Is it 1:1, 2:1, 3:1? What's our mole to mole ratio of iodine to thiosulfate? 1:2, exactly right. So for every 1 mole of iodine, we need 2 moles of thiosulfate. So to link everything together now, to tie this all together, we're going to figure out the moles of thiosulfate via titration. We then know that we have 1 mole of iodine in solution for every 2 moles of thiosulfate that reacted. If you recall previously, we know that this iodine was generated from our hypochlorite anion. So we have 1 mole of hypochlorite generated for every 1 mole of iodine that reacts. Finally, we also know that this hypochlorite, this active bleaching agent, was generated from chlorine. So we have 1 mole of chlorine in solution for every 1 mole of hypochlorite. So we've in effect done a straight conversion from the moles of thiosulfate to the moles of chlorine. And this only works because we clearly understand each of the equations used in each step of this iodometric titration. Do these mole to mole ratios make sense to everyone? Does everyone understand where we got all of these mole to mole ratios from each of our chemical equations? Now, what we're going to do is we're going to titrate a sample of solid and liquid bleach with our thiosulfate solution. So we're going to take a known volume of bleach. So we're going to record the volume of bleach, and we're going to, step 1, record the mass, and then we're going to calculate the density. We're going to save this for later, but don't worry, you do need this. And you'll have to find that in the video. We're then going to dilute our bleach sample. The reason why we dilute our bleach sample is because you really don't want to watch me sitting there adding 100 milliliters of thiosulfate solution. There's no point. If we titrate dilute bleach, we don't have to add as much of our thiosulfate. So we're going to take 10 milliliters of bleach and we're going to dilute it to 100 milliliters total volume. So essentially our concentrated bleach is 10 times as concentrated as the dilute bleach sample we're titrating. We're then going to titrate 25 milliliters of our dilute bleach with potassium iodide under acidic conditions. So we're going to react our bleaching agent with excess iodide. and we're going to generate iodine as the result of this reaction. So we'll see, oh, whoops, sorry. One moment. Okay, so in the end, you'll see in your flask this beautiful color of iodine. And now that we've generated our iodine, we're going to titrate our iodine with a known standard solution of thiosulfate. So in this crude schematic picture, you're going to have your burette, and inside your burette is going to be our thiosulfate. We're going to add thiosulfate to our iodine solution dropwise until we observe a pale yellow color, which is dilute iodine. We're then going to add the starch. We're going to see the blue color of the starch iodine complex, and then we're going to continue adding our thiosulfate until our solution is clear. When our solution is clear, that is the end point, and we're going to record our final volume. Since the end point is approximately equal to our equivalence point, we can relate the moles of iodine to the moles of thiosulfate using our 1-to-2 stoichiometry. Now, so if we know the concentration, of our thiosulfate solution and we know our volume, we can easily calculate the moles by just taking molarity times volume. So expanding out and substituting, we know that the moles of iodine are equal to the molarity of our thiosulfate solution times the volume of solution added. That's what we're figuring out via titration, and times our stoichiometric ratio, which is 1-to-2, which we get from our equation. So this is the classic titration equation schematic. The only thing that's new is we're going to calculate now the moles of hypochlorite by taking the moles of iodine times our stoichiometric ratio of 1-to-1. And finally, we can calculate the moles of chlorine by taking the moles of hypochlorite times our stoichiometric ratio, which is also 1-to-1. So now we have the moles of chlorine. Let's talk a little bit about the parameters for our solution. Now, we took 10 milliliters of concentrated bleach and we diluted it. So we took 25 mils of dilute bleach. Since we diluted our sample by a factor of 10, this dilute bleach, 25 milliliters of dilute bleach, is equivalent to 2.5 milliliters of concentrated bleach. So in effect, we've titrated the same number of moles in our dilute bleach as we did in 2.5 milliliters of our concentrated bleach. Okay, so this is the concentrated volume. So we can now take the moles of chlorine and convert it to grams of chlorine by taking the moles of chlorine times the molar mass. And we can calculate the grams of our bleach solution that we've titrated by taking the volume of our concentrated bleach times the density. And the density is measured for the concentrated bleach. Now that we have the grams of chlorine and the grams of solution, all we have to do to calculate the percentage of chlorine is take the grams of chlorine over the grams of solution times 100%. Does that make sense so far? Any questions so far? So, the only twist when we're titrating our solid bleach is that we take 5 grams of solid, dissolve it in 100 mils of water, and we only titrate a 25 milliliter portion. In other words, we're titrating 5 grams times a 1-to-4 dilution. So 5/4, which means we're effectively titrating 1.25 grams of solid bleach in our aliquot. So if we're calculating the percent of chlorine for our solid bleach, we're going to take the grams of chlorine over 1.25 grams of solid times 100%. Okay, now there's one catch. There's one catch to all this. Before we're able to do our bleach titration, we have to standardize our thiosulfate with potassium iodate. This is known as a redox standard. So just like we standardized our sodium hydroxide with KHP, we also need to standardize our sodium thiosulfate because it decomposes slowly over time and it picks up water over time. So at the end of our redox equation, and you're welcome to try on your own to balance this redox equation, we get the following relationship between iodate and iodide generated. So we're going to mix iodate and iodide, and we're going to generate iodine, and then we're going to titrate the generated iodine with sodium thiosulfate. So my question to all of you is, what is the mole ratio between the moles of iodine and the moles of iodate? What's our ratio? Is it 1:1, 2:1, 3:1? Fundamentally, looking at our chemical equation, even though it's a redox equation, it's still a balanced chemical equation. So what's our mole to mole ratio of iodine to iodate? What's our mole ratio? Three to one. Exactly right. Exactly right. So then, we know that there are 3 moles of iodine generated per 1 mole of iodate reactant. So we're going to take the grams of iodate and calculate the moles of iodate added. We're going to make our potassium iodate solution. We're going to make 100 milliliters of 0.01 molar potassium iodate, and we're only going to titrate 25 milliliters of our standard solution. So there's one thing that you're going to have to figure out in order for the video to make sense. You're going to have to calculate the exact mass of potassium iodate used to make a 0.01 molar solution. That's not shown in the video, and you'll have to calculate this mass, as that's the exact mass that I dispensed when preparing my solution. Now, once we have our 0.01 molar potassium iodate solution, we're going to take 25 milliliters. So you're going to need to calculate the moles by taking the molarity times the volume. So we have our potassium iodate solution prepared. We're then going to add potassium iodide and sulfuric acid, and we're going to generate iodine. Once we've generated our iodine, we're going to titrate with sodium thiosulfate. Now, remembering that for sodium thiosulfate, it reacts with iodine predictably with the following stoichiometry, where we have 1 mole of iodine reacted for every 2 moles of sodium thiosulfate. Okay, so just as a step-by-step, we're going to add our thiosulfate solution until we reach the end point, until our color disappears, just like we titrated our bleach samples. We can figure out the moles of potassium iodate by taking the molarity of potassium iodate times the volume. So we take 0.01 molar times 25 mils, converting to liters. We can calculate the moles of iodine by utilizing our stoichiometry. So we can calculate the moles of potassium iodate, and then in turn, we know that our stoichiometry indicates that we make 3 moles of iodine per 1 mole of iodate. We're then going to calculate the moles of thiosulfate by taking the moles of iodine times the fact that we need 2 moles of thiosulfate for every 1 mole of iodine. Now, to complete our standardization, we're going to take the moles of thiosulfate that we need to add over the volume of the thiosulfate added during our titration. So that's how we get the molarity of thiosulfate that we need for our bleach titration equations. Okay, now just a side note, you may notice that when I've recorded these videos, I was doing the procedure relatively quickly. That's because the titration should be done as fast as possible once you mix your reagents, because iodide reacts with air under acidic conditions. So if you let your sample sit for too long, you'll make a little bit of extra iodine, which interferes with your calculations. That extra iodine is generated from air, not hypochlorite. So that's why I generally titrate pretty quickly once I've added my reagents to minimize the generation of iodine. And with that, that's the complete overview of today's lab. You're now ready to begin and watch the lab video on Canvas.